Hi everyone, welcome back to my channel, The Space Koala. My name is Luca, and today we're taking a deep dive into image calibration. When you Google how to do astrophotography, you'll find hundreds, if not thousands, of guides with all the basics explaining to you exactly what you need to do to start out, also detailing how to do calibration images. Most of these, however, I find do not explain very well in detail what these are for or how they work, or worse, sometimes they even convey incorrect information. Here, for example, we have dark frames capture random thermal and electronic noise of the camera sensor and allow us to subtract it. They can offer significant improvements in noise reduction. While they do explain very well how dark frames should be taken, this reasoning is not entirely correct, because if noise is random, which it is, and they do mention that it is, then by definition it cannot be calibrated out. This seems to be a pattern with all these pages claiming that dark frames contain all the noise that your camera creates. There are also similar misconceptions around flat frames, with a lot of people claiming that these should be taken at the lowest possible ISO or gain levels of your camera. About 90% of the time, just blindly following all these guides will yield perfectly fine images and just calibration frames that work, and you have no issues whatsoever. It is in the other 10% when you encounter some sort of issue with your calibration frames that you really want to understand how they work and how they work together in order to resolve the issue. Sure, the internet is full of information. It is also sadly full of misunderstandings and misinformation. This video aims to clear up any confusion about what calibration frames are, what they're for, when they're essential, and maybe when they're not so essential. Well-calibrated images are an absolute prerequisite for any high-quality astrophotography. They can correct a long list of issues that can plague your images, and ensuring that this way you get the highest quality, clearest, nicest picture you can possibly get of the sky. So let's dive right in. Let's take a look at each type of calibration frame. So we've established that all calibration frames aim to remove some sort of imperfection from your images. As you probably already know by now, there are four main types: dark frames, flat frames, bias frames, and dark flat frames, or what some people may call flat dark frames. Each of these will serve a specific purpose. Dark frames correct for the total electronic signature and dark current. Flat frames correct for dust spots, vignetting, and uneven sensor responses. Bias frames capture the electronic signature of the sensor at zero exposure time. And dark flat frames correct for any dark current present in your flat frame exposures. Now, understanding how each of these work, and more importantly how they all work together, is key to then troubleshooting any issues that come up. Dark frames are often the first calibration frame that beginners encounter because they're so easy to make. Just take a series of exposures with the exact same settings as your light frames, with the only difference being that the lens cap must be on. This means the same ISO or gain, the same temperature, and the same exposure time as your light frames. However, I think because of the not so clear guides online, that a lot of people seem to think that dark frames aim at reducing the overall noise of your image. If it was the case, it would mean that by applying dark frames, we would be able to reduce the overall number of subs that we take, which is sadly not the case. The reason we have to take so many subs, even of bright objects, is that true random noise is random. It's different in every single image, and therefore we cannot calibrate it out. If it could, we wouldn't need to take so many light frames. What dark frames do remove is the full electronic signature of your sensor, which means it includes the readout noise, the dark current if present, and hot pixels if present. From this, the readout noise is actual noise, and this is a property of the sensor at a given ISO or gain, regardless of the exposure time of the frame taken. The real reason we take dark frames, however, is the dark current and the hot pixels of the sensor. If we have a look at what dark current is, we will see that this is not noise at all. This is actual signal we're recording, and it is also not at all random. So by no means can we consider it noise. This is a very important distinction, and I'll get into it in just a sec. As we can see from these graphs, dark current typically increases with longer exposures and higher temperatures. This is also why we prefer cold weather and cooled camera sensors. Dark current is essentially the thermal signal that builds up over the duration of the exposure. By taking dark frames, we can record this signal and then we can subtract it from our light frames. This is especially important for higher temperatures and older sensors that tend to suffer from much more significant amounts of dark current as well as amp glow. Amplifier glow, or amp glow, is another artifact that can plague your images with certain sensors. It is specific to the electronic components that are used to read out the signal from the sensor. The latest generation sensors have largely mitigated this problem, but for everything else, this is still a very important factor to be considered, as this signal comes from very specific components near the sensor. This usually tends to show up in these funky looking patterns on the frames. To give an example, I sometimes use my ASI 183mm or my ASI 1600mm cameras, which use the Sony IMX183 and the Panasonic 32430 sensors respectively. For these sensors, it is an absolute must to use dark frames because the amount of amp glow that they create would just otherwise render the images unusable. These are dark frames taken with each of my sensors at minus 20 degrees Celsius at different exposure lengths. The buildup of dark current and the resulting amp glow is quite obvious. This is another comparison of the same exposure length with the same sensor, but taken at different temperatures. Once again, the difference is quite clear. These tie in perfectly with what we have just seen from the graphs before. Dark current increases as a function of temperature and builds up over time. On the other hand, let's have a look at the dark frames taken with some of my other sensors. I'm showing the same type of comparison here, different temperatures and different exposure times. Typically, when I use my latest generation CMOS cameras based on IMX571 and the IMX455 sensors, seen as how the dark current is so low and the amp glow is inexistent, I tend to just skip the dark frames altogether. And this is a common discussion in astrophotography communities. Surely it is still better to take dark frames even if this amount of amp glow and dark current is low, isn't it? And the answer is not so simple. It really depends on two things. First, are you willing to take the time and put in the effort to do these calibration frames accurately and precisely? And two, are you actually shooting for long enough at high enough temperatures for dark current to actually show up in your image? The first one is important because, as I mentioned before, dark current is signal, which means its accurate value can be hindered by random noise. Therefore, when the amount of dark current is so low, as it is the case with these latest generation sensors, we can actually introduce more noise with a poorly taken dark frame than the amount of dark current we're subtracting. I believe if we use these sensors and we choose to use dark frames, a really large number of them should be taken. I tend to take at least 50 subs for each temperature and exposure time combination to ensure that I average out any random noise. I also only use them if I photograph with a warm sensor, which typically only happens when I'm limited by battery power, so typically when I travel. The second point is really asking if there is even a theoretical benefit to taking these dark frames. Here we see a graph published by the producer of my ASI 6200mm camera, which uses an IMX455 sensor. It shows the relationship between the sensor temperature and the generated dark current. I tend to photograph at minus 20 degrees. However, to stay on the conservative side, let's say I'm cooling the sensor to 0 degrees only, and I'm taking a long 10-minute exposure. At 0 degrees, the sensor is producing 0.003 electrons per second per pixel. So over a 10-minute shot, this would be 0.003 times 600, so 1.8 electrons. This is actually half of the read noise at gain 0 and just over the readout noise at the optimized gain value of 100. From these numbers, it is easy to see that with typical use, dark current is a negligible signal here, and it is absolutely not something to worry about. Of course, potentially we're still left with hot pixels that are left there without the use of dark frames, but with adequately dithered light frames, they should be rejected right out during the integration process. If there are too few light frames, one can still use software that recognizes them automatically to remove them, such as cosmetic correction in PixInsight. Before we move on, let's briefly talk about noise in calibration frames. When I talk about noise in astrophotography, what I really mean is the random readout error for each pixel value. So this is essentially the error of the measurement. As by definition this is random, the only way to reduce it is by taking more measurements, meaning more frames or longer exposures, and average it out. It really helps understand a lot if we put this into the context of what we're actually doing is taking measurements. Say you want to weigh some rice, so you place it in the bowl of your kitchen scale. In this analogy, your pure signal is the weight of the rice, and the weight of the bowl represents the dark current signal you want to remove. You take this measurement a lot of times, similar to how you take many images of a nebula that you will average out later. So we've taken many measurements, and now we know that the approximate weight of the rice and the bowl is about 1,300 grams. Now, in order to get the pure signal out, or the true weight of your rice, we have to subtract the weight of the bowl we just used. This means we have to weigh the bowl only, meaning we have to measure the dark current only. Suppose we use a heavy porcelain bowl and we weigh it just once. We get a value of around 300 grams, but we'll be off by a few grams most likely. This would let us know that the rice is around 1,000 grams, but not exactly. Now, if we weigh our bowl 10 times or 30 times or 50 times, we will get closer and closer to the 300 grams that seems to be the true weight of the bowl. Therefore, we also get closer and closer to the true weight of 1,000 grams for the rice. In any case, even after a few measurements of the bowl, we get a reasonably good idea that the rice weighed around 1,000 grams to begin with. This is similar to taking dark frames with a sensor that shows a large amount of amp glow and dark current. Even by using a small, very limited number of dark frames, we can achieve an extremely significant improvement in the original signal as we remove these artifacts. Of course, you will always further benefit from using a more accurate dark frame because it will allow you to bring out more faint signal. Like if you wanted to measure just a handful of rice, you would really want to make sure that you know the weight of the bowl extremely accurately. On the other hand, taking dark frames with these latest generation sensors with virtually inexistent amp glow and a really low amount of dark current is more similar to weighing our rice on a paper plate. So we do the same thing. We do many measurements and we weigh about 1,005 grams. Then, just like before, we start taking individual measurements of the paper plate. We can see that an individual measurement with the same amount of error as before, as we're using the same scale, can actually result in an error that is a large percentage of the plate itself. Therefore, if we subtract a single weight measurement from our 1,005 grams, it can actually even bring us further from the true weight of 1,000. Only after taking a large number of these measurements do we start seeing a clear trend towards the number 1,000, which we know is the true weight of the rice. This is perfectly analogous why, when using these sensors, it is really not necessary to take dark frames because the amount of dark current, much like the weight of the paper plate, is practically negligible. However, if you do decide to use them, you have to make sure that you do them really well and you take a really large number of them to make sure that you average out any potential errors in the measurement. If you're interested in signal to noise ratio, stay tuned because I'm planning an in-depth video really soon where we'll delve into the best practices and important considerations in much more detail. For now, what we need to take home from this is that the lower the value that we're trying to record, the more accurate our measurement has to be in order to have a benefit. Now that we know all about the importance or lack thereof of dark frames, when to use them and when not to use them, let's move on to the single most important type of calibration frame, the flat frame. These are the ones that you should never skip, not the darks. They correct for dust spots, vignetting, and uneven sensor sensitivity. I've seen quite a few astrophotographers online proudly claim that they don't need to take flat frames because they keep their optics clean and any potential vignetting in any way can be removed in post-processing. But it is important to consider that flat frames do more than just that. So first of all, dust spots can appear anywhere in your imaging train, on your sensor, in front of it, on the glass, on the telescope itself, on any filter that you use. You're gonna get them eventually, no matter how careful you are. But flat frames help us remove them by letting us take a picture of the imperfection and just use that to remove these from our frames. Very similarly, flat frames also correct for vignetting, which is the darkening of the outer edges of your image due to the optical design of the telescope. And this one is especially important for those of us using larger sensors. For example, look at this image of mine here. In all honesty, it looks kind of horrible. There are dust spots, there's vignetting from my 2-inch filters that are just a little too small for my full frame sensor. And since this was a relatively fast focal ratio telescope, there's even a small shadow from my off-axis guider. Still, this is absolutely nothing a well-made flat frame cannot take care of. This is exactly what I did, and this is the master flat frame from that imaging session. Finally, this is a single flat calibrated light sub, now void of any hint of vignetting or dust specks. There is no way anyone would have been able to do this in post-processing, and neither should there be a reason to try so. Similarly to the dark current we've seen before, the differences in the illumination of the sensor resulting from these artifacts can be reliably measured. So we have every reason to take good quality flat frames for every single imaging session. As we know, to take flat frames, you'll need an evenly illuminated surface, such as a light panel or the sky at twilight. Ensure that the light is uniform and it covers the entire front of the telescope. You can use a white cloth or t-shirt to make the light even more uniform by putting it in front of the telescope. I tend to take around 30 flat frames per filter to take my master flat. Of course, once again, you can benefit from taking many more because we do have noise in these flat frames. However, the signal present in the image is so much stronger compared to the noise that we're usually able to get away with using fewer of them. It takes like absolutely no time to take them though, so why not create the proper series every time? So make sure you take a series of them without changing any of your settings or anything in the optical train. The only thing that changes here is the exposure time. To determine the appropriate exposure time, in my experience, any astrophotography software that offers the option of auto flats does a really great job, and I've never had an issue using those. When I take flats with my mirrorless camera, I tend not to use any astrophotography software. I do everything manually, so I just use the histogram of the camera and just ensure that the peak is around the 2/3 of the histogram bar. As this video is more about the theoretical side of how calibration frames work, I will not go into more detail on how to do this. Instead, I will link a really good guide below the video that will explain in much more detail how to take flat frames in the manual way. Instead, today, I would just like to focus on one very important thing on flats, and that is the gain, or the ISO. There's quite a few guides out there that recommend taking flats at the lowest possible ISO or gain value of the camera. In general, I believe this is recommended because this way we can ensure that the flat frame is long enough for it to be adequate. For DSLRs, this is crucial because, especially over time, the mirror flip mechanism tends to get a little lazier, a little slower. So if we take the flat too quickly, then one side of the sensor will be illuminated for a longer period of time and the flat will not be even. Adequate flat frame length is also important for these modern astro cameras because they typically have rolling shutters. So especially if you're using any type of a light panel, like an LED panel or an EL sheet, this is what I do. Since it's electronic, it's always going to have a frequency. Now, if that frequency is not high enough, then the rolling shutter will record the light flashing even if you can't see it. And this will result in these very nice stripy images, and then that will transfer right on to the calibrated light frames, and that's going to be an artifact you're never going to be able to remove. However, the correct way to increase the exposure time of your flats is not by decreasing the ISO or the gain, it is by decreasing the intensity of the light source, which means if you cannot regulate your LED panel, just put a sheet of paper or something in between and you're good. This is what I do. This is necessary because in an ideal world, light frames and flat frames should be taken at the same ISO or gain. The reason behind it is that in addition to removing vignetting and dust specks, flat frames also do a third very important task, and that is evening out the sensor response. Every single pixel on your sensor may have a slightly different level of responsiveness to light. This difference is also multiplicative, just like the dust specks and vignetting, so it can just be removed by using the same exact flat frame. However, this responsiveness can vary between the different ISOs, and therefore we have to use the same value. This feature is most important to people doing photometry. Photometry is the measurement of the brightness of stars, most typically when studying variable stars. When studying these, even the slightest differences in brightness have to be accurately recorded. Flat frames correct for inconsistencies in pixel response, therefore ensuring that brightness measurements are accurate across the entire field of view. While I have personally never tried it is important to know that astrometry is not just for professional astronomers. Amateur astronomers can contribute valuable data to the scientific community by accurately measuring and reporting star brightness variations. For them, accurate flat field calibration is even more crucial than in astrophotography. I mentioned that all these artifacts are multiplicative, but what does that mean? What it means is that all these factors we just mentioned actually modulate the incoming signal, meaning if you have vignetting in your imaging train, that is not just a fixed delta making the outside parts of the image darker by that much, but its exact value will depend on the incoming light. This is why we cannot simply subtract or add flat frames. Mathematically speaking, we have to divide by them. If this idea is a little difficult to grasp, think about it like this. Say you have your imaging train with vignetting, then you put the lens cap on the front of the telescope and you take a frame. Would it be correct to flat calibrate it by adding or subtracting a value from it? No, it wouldn't, because there's no vignetting, because there's no light. If you subtracted something, you would actually end up with negative values that you can't have. However, it still works if you divide your picture with your flat frame, because you divide 0 by anything, it is still going to give you 0. So the calibrated image will be correct. Now let's see how these frames are used in the calibration process. I'll be using PixInsight, but the process is exactly the same in any other software. The first step is to subtract the dark frames from the light frames to remove the dark current and electronic signature. This removes any fixed pattern noise like hot pixels as well. In the next step, we'll be dividing with the flat frame. This should normalize our pixel response and even out any optical issues we have. So we expect a perfectly nice and calibrated image, right? Well, no, this is what we get instead. There is something very wrong with it. It is easy to figure out what went wrong if we try to think about what we did specifically. We took a picture, we removed the electronic signature of the sensor, then divided it with another picture, but we forgot to do the same thing here. We were not just dividing with the pure flat signal, but with a larger value due to the electronic signature that is also present in the flat frames. Enter bias frames or dark flat frames. True bias frames capture the sensor's electronic signature at 0 exposure time. This is physically not possible with CMOS sensors because the 0 exposure time idea comes from back in the CCD times where it was a possibility. So what we do is we do the next best thing, which is putting our cap on the sensor and taking a picture with the shortest possible exposure time. On all of my cameras, this is 32 microseconds. Technically, it is like a dark frame. However, it's virtually guaranteed that there's no thermal noise, there's no amp glow, there's no dark current, because there's physically no time for any of that signal to accumulate. Important thing, as we've seen before, if we want to calibrate for small values, which is the case with bias frames because we're calibrating out the readout noise, the lower the value we want to calibrate with, the more important it becomes that we're extremely precise. And this is why I take 300 bias images to then create a master bias. Then I use this same master bias to calibrate all my frames. My flats are typically short enough and they do not contain a lot of dark currents, so they're perfectly calibrated by the bias. And as I mentioned before, very often I tend to opt out of dark frames altogether. In those cases, I will use the same master bias to calibrate the lights before a flat field correction. As bias frames quite literally take a fraction of a second to do, there's really no reason not to take them really well, take a bunch of them, and then use that master bias for a really long time. Here, I would like to mention dark flat frames, or as some people like to call them, flat dark frames. These essentially do the same exact job as bias frames, so they calibrate the readout noise out of flat frames, but in addition, their aim is to also subtract any dark current or amp glow or hot pixels that could potentially be present on the flat frames. It is a good idea to use them with sensors that produce a lot of that signal, and especially if the flats are taken over a longer exposure time. So now we can repeat the same exact thing as before, but now with the already pre-calibrated master flat, and the result we get is indeed much better. This is what a perfectly calibrated light frame should look like. No sign of issues from the sensors such as amp glow, and no vignetting or dust specks remaining. To summarize, good calibration frames are essential for high quality astrophotography, while modern sensors make master darks not as important. Flats and biases remain indispensable. Biases can be pretty much taken at any time, but flats are trickier because you always have to take them at the same time as your lights. So my trick to ensure that I always have them is that I take them at the beginning of my session. I used to do what most people do, just take them at the end of my session, just wait until it starts getting light and then take them. But I've had far too many incidents when there was sudden incoming clouds, rain, or whatever reason that I had to immediately pack up. And obviously there's no time to take flat frames, and if you don't do them, then those images are essentially lost because you cannot recreate that once you've taken the optical train apart. So what I do is I go outside as soon as the sky is dark enough for me to see stars. I align my telescope, I rotate my camera in the direction that I want to take my images in, and I have plenty of time to take all of my flat frames before astro dark hits. This way, no matter what type of natural disaster hits throughout the night, at least I know that whatever light frame I was able to take, I will be able to use it because I already have the calibration frames for them. So in my opinion, anyone who doesn't have a fixed setup, a fixed observatory, should follow the same process to avoid bad surprises. And then all the other calibration frames can be taken at any time really. So in my opinion, I wouldn't waste time under the stars to do those, especially darks, because they take a really long time. So we should all invest some time to create a really good master bias. If you want to use the darks, invest a lot of time to do them well and be real precise with the flats. It is infinitely easier to post-process images that have no calibration issues, so we should all invest some time to build up a precise and nice master bias and master dark library and do those flats nicely when we're out under the stars. That is it for today. If you found this video helpful, consider subscribing to the Space Koala and keep an eye out for more upcoming in-depth videos like these. Happy summer solstice, at least here in the Northern Hemisphere. Darkness is finally going to come back, and clear skies, everyone.